Good morning, sir. Anupam, sir, good morning.
Morning, good morning. Good morning. How are you?
We are starting the session in 5 minutes.
Huh? Sure,
Waiting.
sure. I will also take some time. Maybe around 9:30, 9:35.
Okay, sir. We'll start at 9:35.
Okay, sure.
Good morning, sir.
Hello, good morning.
Yes, sir, Tito.
So, how is everything there?
It's good, sir. Thank you. How is going over there in IT Ropar?
Yes, yes, it is going on good. Good that it is online.
Yes.
Today it is very too much fog.
Oh, yeah, yes, sir. That's why we are planning that the morning session is always be online because it's
Mm.
very difficult to reach at the place.
Yes, yes, yes.
Either you have to come in the one day before.
Mm-hmm.
Course, to spare that much time. So, sir, we have sir hybrid mode. We'll have some participants in online system, and we'll have some participants over there in the offline system.
Okay.
We'll start the session just in a minute.
No problem. So whenever it is like so, I will start sharing. No.
Yeah, yes, sir. I will introduce you. After that, we'll start the session. Just give us 2 minutes more.
Yeah, yeah. Take like no hurry. Okay.
Okay. Okay, so we'll start with the session. Good morning, participants. Good morning, sir. Thanks for accepting our invitation. So, sir, I will give brief introduction about the person. Now, Dr. Anupam Agrawal received his bachelor's degree in mechanical engineering from Madan Mohan Malviya Engineering College, Gorakhpur, master's degree in mechanical engineering from Indian Institute of Technology, Kharagpur, and PhD in mechanical engineering from Indian Institute of Technology, Kanpur. He worked as postdoctoral research fellow at International Center for Automotive Research at Salman University, USA, for 2 years. After his postdoctoral stint, he joined as an assistant professor in 2010 and as an associate professor in 2015 in the Department of Mechanical Engineering, IIT Ropar. Dr. Anupam Agrawal has worked in the areas of formings, micromachining, additive, and advanced manufacturing processes. Thank you, sir. Thanks for coming. And I will hand over the system to you for your expert talk. Thank you, sir.
Thank you for nice introductions. So I will start the slide sharing now. So hope the slides are visible.
Yes, sir, it's visible.
Maybe I'll switch off first the video because it will take much of bandwidth.
No issues.
Okay. Yeah. So yes. So welcome to all the participants, and this is the third day of the workshop. This recent trends in additive manufacturing. So hopefully you already have a lot of introduction about in general what the additive manufacturing processes are and what are the capabilities of these processes and so on. So like I need not go about additive manufacturing processes. And yeah, participants, if you have anything to discuss or you want to ask any question, you can also ask during the presentation. I want it to be interactive if possible, so that like you need not keep the questions for the end, and then maybe you may forget and I may forget the context. So you can keep asking the doubt as and when they arise, and also towards the end also in general discussion. So the topic today is specific to selective laser melting, which is a powder bed fusion based technique. So the topic here is, I'll turn on the pointer. Maybe error. Okay. So the topic today is understanding role of melt pool characteristics in selective laser melting based additive manufacturing processes. So the selective laser melting based processes, they are characterized by certain typical characteristic, and it all depends upon how the melt pool forms. So we will see in detail what does it mean and how does this melt pool decide the quality of products that is obtained using the selective laser melting based process, additive manufacturing processes. So firstly, like initially some very brief introduction about the SLM. We start with the additive manufacturing, as normally I do, is to brush up whatever the additive manufacturing understanding. The term additive manufacturing, as you might recall, it all started with rapid prototyping. So there was a need to rapidly create systems or prototypes which can later on be commercialized. So like conceptual design, and then it was rapidly prototyped. So earlier there used to be skilled craftsmen who used to do all these things, but there was a need to make complex part and also make it rapidly. That means in short span of time. So it all started with this rapid prototyping. The additive manufacturing, the start was with this, where the part was represented using a CAD file and the prototype using some other material just to realize how the design would look like was made. However, this term, so earlier it was known as rapid prototyping. However, this recently formed technical committee. So this ASTM International Committee for Additive Manufacturing, they keep on upgrading their technology, their terminology, both. So they have adopted the term additive manufacturing. So rather than the term rapid prototyping, or there are so many other commonly used terms that we will see a list of terms which mean the same: additive manufacturing or 3D printing or rapid prototyping or so on. So they have adopted this term additive manufacturing as the most appropriate one for representing this technology. And the basic principle of this technology is that a model which is initially generated using a 3D CAD system can be fabricated directly without the need for any further process planning, without the need of any other tooling, process sequencing, and so on. So just design and print, as we just type any letter and then directly give command for printing and it gets printed. Similarly, a 3D model will get printed, is the concept for additive manufacturing. A brief comparison, like why additive or subtractive, and what is the difference. So if we see, still much of our current manufacturing is subtractive. So the block on the right hand side where my cursor is right now, it represents that for subtractive manufacturing we start with a block and we remove the material as we move down and then make the part which is shown on the left. Whereas the additive manufacturing, as opposed to subtractive, it starts adding layers. So if you can see here, there are several layers added one up after the other. So same layer thickness or different layer thickness as the need be, and layer by layer this complex object is made. So there is almost no wastage of material, apart from these places where the excess material is there. So we may need to remove small amount of material, but there is no material wastage. Whereas when we cut this piece, there is a huge material wastage, plus the design complexity is quite limited. So additive versus subtractive, there's a huge debate whether the additive manufacturing processes can replace the subtractive manufacturing processes or not, and so on. So like there are like kind of arguments on both sides. We can probably decide towards the end of this lecture which one is better, or a combination would be better. So as I said, subtractive, a lot of waste. So we need to make the material, the object. We start removing material and then we get a 3D object with a lot of waste. Whereas in additive manufacturing, we start with a powder material, as in case of the powder bed like SLM we are going to discuss today, or some other form of material like a solid wire, pellets, and so on. So many other forms, so many forms of material as a starting material for additive manufacturing. And we layer by layer add, that is additive manufacturing, we put it in an additive manufacturing machine. We get the object with very small amount of waste, as I said, some finishing, some polishing, and so on. So there are so many limitations which have forced the researchers to work in the area of, or to develop the additive manufacturing processes. Some of the things we have seen here, like a lot of waste, very small waste, but that is not the only issue, because this waste which is there in subtractive manufacturing processes, many a times these waste can be recycled also. So it's not that just based upon the waste of material, the additive manufacturing process, they have an edge. They have an edge in different domains. Why? Like, consider this kind of a example. I think this is a very common example which is shown by several presenters, but this is really very impressive one, where it shows that, see, if one has to make a very deep cavity using the current subtractive techniques, it is difficult. Why? Because what would we need is a very long slender end mills or the milling cutters, which would be required to cut this deep hole. And as the depth of this hole increases, it becomes very difficult, very difficult to machine further because of the inherent vibration of the tool, as well as vibration on the wall that it is machining. Similarly, there are features which, when there is an undercut or some feature which is not available or not approachable by the tool, it is difficult to machine. This base cannot be machined unless we flip the cup upside down. That means in a single setup it cannot be machined. So when we reposition any object during machining or making process, then the accuracy is lost, and these sharp corners, etc., they are difficult to make using conventional subtractive manufacturing because of the uh, tool geometry, because there is a certain tool radius always present. It cannot be a very sharp tool because of tool failure and other reasons, stress concentration and so on. So sharp internal features are difficult to machine because of the limitations of subtractive manufacturing, but all of these can very easily be done with the additive manufacturing process. So there'll be a slide later on, just 2 or 3 slides later, where we can see how the slicing model of this cup will help us making it using the additive manufacturing processes. There are several distinctions between additive manufacturing and CNC machining, like set of materials which can be used for additive manufacturing and CNC. They are quite different. The initial raw material, which is in the form of a bulk, billet, and so on in case of CNC machining. In case of additive manufacturing, the starting shape of material is quite different, maybe powder, pellets, and so on. And at the same time, the material choices for additive manufacturing is still limited. Not that every material can be used for additive manufacturing, whereas the domain of materials for CNC machining is unlimited. Almost all the metal, non-metal, like when we say almost, that means not all, but almost all metal, non-metals can be machined using the conventional subtractive machining using CNC. So there's a gap. Additive manufacturing lacks in choices of material. The speed of fabrication, once the design is there and then we want to make hundreds, thousands of products in a day, CNC machining is the way we can go. Additive manufacturing is a slow process. Why? Because we need to make the objects layer by layer, and each layer requires a lot of time to get fused together. So speed is an issue. However, when it comes to ease of use is good for additive manufacturing because almost no skill is required. We need a starting model for both additive manufacturing and CNC, but after that, there's nothing which is required, almost nothing which is required in terms of skills, because once the software is there, it will automatically do the slicing and other things for default setting. So ease of use is there. Accuracy, size limitation, geometric complexity. So geometric complexity is where AM, additive manufacturing, wins any complexity it can make with the same ease. Size limitations in an enclosed environment. So very difficult to make very large products. So the sizes of the products which can be made in additive manufacturing, they are quite small as compared to the huge sizes which can be made in CNC machining. Accuracy wise, now they are neck to neck because additive manufacturing processes have evolved quite rapidly, and then the accuracy, even though CNC machining might have an edge, but additive manufacturing processes are not far behind. In terms of programming in CNC machining, we need G codes, M codes, the codes which are required to run the CNC machine. Similarly, for additive manufacturing, we need certain knowledge about the additive manufacturing software for that particular process. So both are comparable. Cost-wise, additive manufacturing processes still they are on a highly costly side. However, when it comes to customized products, the products of a specific kind for a small batches and so on, their additive manufacturing processes might compete with in terms of cost with CNC machining. Otherwise, CNC machining usually will cost much lesser than the additive manufacturing components. As comparing environmentally friendly, so less wastage in additive manufacturing than CNC. So here the environmental friendly is there additive manufacturing, but when we use lasers, so which are not very much this environmentally friendly, so in laser based processes a little concern about environment or environment friendliness is there with respect to additive manufacturing processes. So all these I have said, flexibility in design for additive manufacturing, not much of expensive tooling, dimensional accuracy is there, comparable to CNC, wide range of materials, however, still not as compared to the CNC, not comparable to the CNC machining, and minimal waste, green manufacturing, cleaner environment apart from where we use high intensity lasers. So all these are the advantages of additive manufacturing processes, and that is what the objective of this course also, this recent trends in additive manufacturing, that we should know the capabilities of additive manufacturing and should try to use this additive manufacturing processes more often than the subtractive manufacturing processes. And then limitations also I said in the first slide, the previous slide itself, that the part size is a problem, material choices, even though they are there, but not that all the materials can be used, especially the non-weldable metals cannot be processed, because the basic requirement for a layer to form is that it should easily form or fuse together. That means it should have good welding or weldable properties, which if it is not there, it cannot be used. The other issue, okay, that I must tell, because this is one of the things that I would be presenting when I would tell about the melt pool characteristics, is that the material properties which are obtained in additive manufacturing processes, they tend to show an anisotropy in z direction. Like, we can easily think why it is, because when we make anything layer by layer, so one top of the other, that means the strength in the direction of the place. I'll go to that slide. So here, when we are making this layer by layer, so this bonding strength, that decides what would be the strength in the direction, which is, let's say, z direction, where my mouse is moving up. So in this direction, the strength would be much lesser as compared to if we try to stretch it in this direction, x and y directions. So the anisotropic property is very strong in case of additive manufacturing processes. So strong anisotropy in z direction, construction direction. The porosity, let's see, it can be reached up to 99.9% of porosity of density, but usually there are a lot of residual stresses as well as internal porosities, which are a typical characteristic of additive manufacturing processes. Mechanical properties, they are better than the parts, that is better than the casting based methods, but not as good as the formed or wrought parts. So that is another limitation, that the part properties are usually inferior to the bulk metal or bulk products. Just a brief about the additive manufacturing evolution. So when and how it was evolved. So if we just go bottom first, we see 1988 first commercial rapid prototyping system was made. However, it all started with almost more than 200 years back, in 1770, with the Industrial Revolution, and before even that, the mechanization of things. So, like the first machines, they started coming, but it then waited almost 150 years before the first computer was made. Then the first numerical control machine, first commercial laser, which is usually a requirement in additive manufacturing, machine, a commercial robot, and what was remaining after this was a graphics system, because for the other basic requirement apart from this numerical control and other thing is that we must have a robust computer aided design system. So once this was invented and then the graphic system was in place, so it did not take much time to get the first rapid prototyping system. The first rapid prototyping system, it was a SLS, stereolithography machine made by 3D Systems. So that was the first one which changed the world as we see today in terms of manufacturing processes. So here, it was just a photopolymer that they could make using this rapid prototyping system into very smaller parts. But that was a revolution. And after that, these AM applications have not stopped, and then the projection, if we see, so 1988 to 1994, typically it was used for rapid prototyping. Later on, it turned into rapid casting, rapid tooling. Then the there was a path breaking that not just for making prototyping or rapid tooling, the usage of additive manufacturing parts for direct construction of useful components. So AM for automotive started, AM for aerospace, it started with polymers. Then later on, it all kind of see in 2011, if you see aerospace for metals as well, medical, medical implants, both polymers and metals. Then it started to go in other domains. So we could see that, see, it can not go very high in size, but it can always go customized and smaller in size. So nano manufacturing, nano level manufacturing, then it started in the architecture and civil construction also. So a lot of videos you might see over YouTube, internet, and other resources, that a lot of houses are also getting 3D printed. Yeah, those are kind of a little far-fetched ideas, but I would say that, see, the concept derived from the additive manufacturing only. Then biomedical implants with all possible materials and all possible complexities for direct usage, not just for prototype, started. And the projection is there that in situ biomanufacturing, which has not yet picked up, but it will pick up in next 2 to 3 years, and full body organs directly printed using additive manufacturing in next 10 years or so. So all these show the capability of additive manufacturing processes in terms of applications, and the limitation of additive manufacturing processes, which was that it cannot compete in terms of mass manufacturing with CNC, but it can compete in terms of the customized products, the patient specific implants, or in terms of aerospace, where only a few such products are required and then the design changes. So for any custom fabrication where flexibility in design is required, the additive manufacturing is the go word. That means one has to go with this additive manufacturing for different applications. And as I said, that additive manufacturing, it is known with different other terms also. So this is just a brief of that: additive manufacturing, additive layer manufacturing, additive digital manufacturing. These are other names. And many a times, my favorite term is layered manufacturing. Why? Because it is all, it tells the correct thing about this process. That is, it is adding the material layer by layer. So layer based manufacturing, layer oriented manufacturing, or just the layer manufacturing. Rapid technology, rapid prototyping, rapid tooling, and rapid manufacturing are also some of the common name. Digital fabrication, digital mock-up, and I think the by far the most popular term till now is 3D printing. Still, apart from additive manufacturing, the most common or most popular term is 3D printing. So wherever we read in newspapers, news articles, we say that okay, 3D printed material, a 3D printed product, 3D printed house, and so on. So 3D printed printing is another name. Direct manufacturing, direct tooling. So there are so many names depending upon what is the preference, what is the focus of that technology. Names are given. Initially, which we have seen, what are the difficulties when we make it using the subtractive manufacturing, whereas when we make it using layered manufacturing, so this shows very thick slices, coarse slices. Here it shows using a fine, small thickness, very thin slices. So it is very smooth. It is not as smooth, but the part features are all preserved. So it is as easy to make this straight portion or this complex portion, only that sometimes we need support for making the extended portion like this. So those are other issues with the additive manufacturing processes. But if we see from the viewpoint of complexity, unlimited complexity can be achieved without being worried about the design. And typically these are the generic processes which are there in case of additive manufacturing processes. So we start with a CAD model, we convert it using the common format STL, stereo lithography, or standard triangulation language. So this we convert it into STL file. Then we transfer the file to the machine. The machine does the slicing and so on. It prepares the part, which can be a form of this machine setup. Then the next step is build, fifth. So here there is hardly any user interaction. Automatically just prints. Once it is printed, the part is taken out and then it is removed from this platform. So normally, like, it is easy for FDM based processes to remove the part. However, when we talk about powder bed fusion based processes in SLM, what we need to do, we need to print it on this build plate. So build plate has to be taken out, and it has to be cut either using EDM, wire EDM, or some conventional machining processes. The part has to be cut from the base, and then it is useful. So removing process may be very simple or little complex depending upon which variant of AM we are talking about. And then it is ready for the application after maybe some smoothing, some post processing, some polishing, and so on. It is ready for this. So from concept, CAD or concept, up to the final application, there is hardly any skill required from the point of view of the process planning. See, obviously the CAD design and other things should be perfect, and if there are any in between processing are required, so some amount of skill is required, but not as much as a subtractive or CNC machining skill which is required. There are so many other related things which are there, which like an additive manufacturing technology requires. So knowledge about the STL file format, the CAD system, and so on. The reverse engineering technology is also, like, see, when we start with a product which is already there and we want to replicate those products, so first we need to capture the CAD model from the part itself, so reverse engineering that kind of technology, and then we build it directly using additive manufacturing machine, computer aided engineering, and more recently this haptic based CAD has taken up a lot of news. Why? Because see, in here, see, for defining any of these curved surfaces using conventional CAD model, we require certain mathematical form of curves, like either Bezier, B-splines, nerves, and so on. Without mathematical representation of curves, we cannot make a CAD model. However, when you see an artist making drawing, So these artists, they do not when they draw, they do not draw based upon the some mathematical calculation, no control points, nothing. They just keep drawing, and when they just keep drawing, they make very complex these curves which cannot be defined easily by the mathematical representation of curves. Haptic based CAD, it means that using a joystick or a virtual reality environment, the artist can create these complex geometries on the computer screen directly, and then based upon that the CAD model is made without using the mathematical representation of curves. So like fairly complex, more complex products can be made, because the capability of additive manufacturing can be utilized completely when we make very complex products. So this haptic based CAD, which is upcoming technology, is taking a lot of news today, nowadays. Coming to the classifications, and then we will move to our particular set of process. The rapid prototyping, so this material addition, the starting material could be either in liquid form, discrete particles, or in form of solid sheets. So in liquid there are different processes, uh, like SLA and SGC, FDM. So where it is all melted. Discrete particle, so like powder based, SLS, SLM, 3D printing, and so on. And solid sheet based, like LOM kind of, this laminated object manufacturing, this ultrasonic based processes, and so on. So there are primarily three class of processes, with distinguished based upon the type of, or the phase of starting material: liquid, powder, or solid. And what we are focusing today is on discrete particle, where the starting material is in the form of powder. There's another way, the same thing, this classification can be represented. So there's a researcher who has proposed this FAM, that instead of representing it in the conventional, this traditional way, it is better to represent it in this way, that the starting material, and depending upon the kind of scanning technology. So if there's a liquid polymer, 1D channel, like just one UV ray which is kind of scanning and making the part, SLA or dual beam, or an array of these beams, or a layer, one layer at a time. So depending upon what kind of scanning strategies are used and what kind of material is used, so in a 2D array kind of classification, so the discrete particles, and then depending upon what kind of scanning strategies, similarly for molten material, metals, and solid sheets. Metal mean like not just metal, the polymers and other metals which are presented in a molten form, or this first one is the liquid photopolymer kind of process. So this is another way people classify the additive manufacturing based processes. Now coming to the class of processes that we are dealing today. So this powder bed fusion based processes, it is a layer by layer technique, where the materials are fused together using a thermal source which melts and fuses the powder particles to a prescribed region of each layer. And most commonly this thermal source is in the form of lasers or electron beam. So one of these are generally used. And the first commercialized additive manufacturing process based upon the powder bed fusion was developed at the University of Texas at Austin, and it was based upon the selective laser sintering based process. The basic approach for all these PBF, powder bed fusion, so we'll normally call it PBF processes, they try to enable the machine productivity enable different materials. So this SLS actually was the first, like if I remember correctly, it was the first process which could use metals, polymers, and ceramics, all the materials as like in a single technology. So enable different materials to be processed, and like see later on a lot of improvement in this basic SLS technology was there to avoid these patented features that was done when the first initially the machine was made. So a lot of changes after that have been made. The initial was for plastic prototypes. However, the PBF processes are now used for polymers, metals, ceramics, and composites. So all of these, so like I'll go to maybe the process this here. So all of this, they can be made using the same ease or same difficulty, as you can say, like as you would like to understand. The they all start with a powder bed, which is supplied layer by layer. So here this is in between, looks like the part is in the process of being made, and once a layer of powder using set of rollers or knife or some form of spreader is spread over the platform, the laser beam traces only those portions which are to be fused together. The excess powder, it gets taken up in this excess powder take up bin on both sides. So this is a dual recoater. So in one layer the roller will move like this, the other layer the powder supply bed will be this, and then the powder will be supplied from this side, and so on. So this way the productivity is more, like otherwise the roller has to come back all the way, and then that takes a little more time. So this is a dual powder supply bed kind of system. So this SLS based powder bed based technologies are the same whether we talk about SLS or any other technique. So there are so many techniques like SLS, selective laser sintering, SLM, selective laser melting, electron beam melting, and like a slight variant of this line wise an array of 1D channels, as we have seen during classification, or a 2D layer directly printed for polymers. So but for metals usually SLS, SLM, and EBM. So as we were here, so all PBF processes, they involve the spreading of the powder material over previous layers. There are different mechanisms to enable this, including a roller or a blade. So whatever we are actually using, either a roller or a blade, that is required to spread this. The bonding mechanism, so like I'll not go through all of this, but what I will tell here is that the SLS, in SLS, the selective laser sintering, the term is sintering, not melting, as in case of this. So here the point, the bonding takes place because of the sintering of the surrounding powders. So when the laser beam indents here, the powder particles, that they get heated up, and because of this heating they start to get sinter. So as in powder metallurgy we talk about compaction and sintering. So compaction is provided by a roller while it is putting the layers, and the sintering is obtained because of the heating below melting point temperature, not above or not at melting point. So this selective means only those places where the laser beam will incident, those places will get sintered. So in SLS, SLS fuses thin layers of powders which have been spread across the build area using a counter rotating powder leveling roller, and it gets fused. Usually all of these things, this part building process, it takes place inside an enclosed chamber with nitrogen gas, or in case of highly reactive metals, instead of nitrogen gas some other inert gas like argon is used. so that the oxidation can be completely avoided, so to minimize the oxidation or the degradation of powder material. So either nitrogen gas or argon gas, depending upon which metal we are printing using this SLS technique. Now we move to SLM, so which is the advanced version of the SLS machine. So here all other system is the same. Instead of low intensity or low energy laser, here in case of SLM, high energy laser is put, and the metal powder temperature is raised up to melting point temperature, and the bonding between the layer and within the layer in the powder particles, it takes place because of the fusion, melting and solidification of the powder particles together. So in SLM, the process is nearly similar to SLS. The only difference is that in SLM, powder material is being heated up to the full melting and resolidification of the final fabrication of the full melting and resolidification. This is how the part layers are formed in case of SLM, whereas in SLS only the sintering. So now we can think which one would give us more strength, SLS or SLM. Obviously, like, see, when it is melting and fusing together, it will be having more strength, just like see, it is more like a welded or a casted product. SLS is more like a powder metallurgy based products which are having lot of porosity, lower density. SLM products, they have almost 99.9% density. So SLM products, they are much better in terms of mechanical properties because of full melting and resolidification. Now, how it is different further, as I said, lasers with wavelengths better tuned to the absorptivity of metal powders, they are used for SLM. That means high energy as well as those wavelengths of laser which are getting absorbed in the metal powders easily. So not that all wavelength can be absorbed in the metal powders equally. So if absorption of laser is more in metal powder, the metal powder will get heated up quickly up to the required temperature. So these lasers which are used here, they have better absorptivity as compared to the other wavelengths of laser in the metal powder which is used. So the temperature gets heated up, the temperature gets the temperature rises far quickly. So usually these ND-YAG based lasers are used instead of this CO2 laser which are used in case of let's say SLS. So ND-YAG based lasers are used in case of this SLM, and the SLS compared to SLS, SLM is even faster because sintering takes like say sintering, even though it happens over lower at lower temperature, but it takes some time, whereas melting is and resolidification is relatively faster. However, at higher energy cost because we need to raise the temperature higher, so it has poor energy efficiency, the like as compared to SLS process. So SLS process have better energy efficiency but lower mechanical properties. SLM the ability to produce parts which are having better mechanical and metallurgical properties. And both the processes, they use either a roller or a blade to spread the new layer of powder over the previous layers. This shows another way of representing this schematic of the SLM. So here you see this feed container, the part getting made, and so on. The layer by layer manufacturing, the selective laser melting, which is nowadays in almost 90% of the almost all the powder bed created by Selective. Are on-demand manufacturing, customization and personalization. Any design, any thing, any design changes as per the need of the consumer can directly be done, but just by changing the initial CAD file. No need for exceptional tooling, reduction in material wastage, novel components and structures. So very unique structures, very unique components of complex geometries, heterogeneous composition. So materials in different layers, like even though not much many of the commercial machines can do that, but theoretically speaking, each layer can be made using different materials. So heterogeneous compositions. Novel structures like honeycomb is just one of the simplest structures for additive manufacturing, for subtractive manufacturing to be made. So heterogeneous compositions, novel structures, etc. can be made using the selective separating process. The other key features is suitable for both metals and just a message. Uh, something
Sir, in this SLS melting is not melting, the centering process, can we do for the zirconia oxide centering layer by layer?
zirconium oxide.
Yeah.
Like this is a particular metal. Like if it can be presented in powder form. Definitely yes.
That oxide can also be layered.
Of a compatible inert gas, so that the oxide does not react during the process with other available gases in the air. So the enclosed chamber has to be made accordingly. Otherwise, yes, definitely it can be. We have a machine. This is
Centering.
Talking about centering. Centering means are very common nowadays. See, whatever SLS can definitely that.
Okay.
You're welcome. Yeah, good. Even like the audience are there who are listening, because it is sometimes quite boring when you're just speaking, looking at the screen.
No, sir, it's a quite interactive session.
Yeah, thank you. So key features. Yes, any other question? Because while in the full screen mode, I cannot see if there is anything written, so I have to go back. See here. No.
Anyone have any other query? Please ask.
Yeah, you can ask without raising your hand, because I cannot see the hand while I'm in the full screen mode. So it's okay. So I'll keep proceeding. But if there is anything, you just, instead of just raising your hand, you can unmute and ask. So the other key features are like easy to make complex parts, less material wastage, and so on. These are just to show some of the complex geometries. See, we cannot think of this component with subtractive technologies alone. The kind of internal features, internal structures that are made using this layer by layer technique in SLM, it is unique. Similarly, making this machining of the turbine blades, it was kind of a huge issue in, and there are so many research that is done in conventional manufacturing for making such products, which are fairly simple. I would not say the simplest, but fairly simple. Like why I'm not saying the simplest, because many of these, like see, all of these things, they would require a lot of process planning for additive manufacturing, also for making the support structure. Because see, all these hollow structures which are visible from outside, or those which are there inside, they cannot be made without proper planning of the support structure. Similarly, here the curved surfaces, while they are being made, the support is required. Otherwise, there will be no stability of the material while it is being made. But see, when we say powder bed fusion based processes, normally no support structure we say it is required. But because of the added weight of these layers, the powder particles which are there underneath these layers, sometimes they are not able to completely support the weight of these heavy layers. So that is why the support structure is when we study in principle the powder bed based processes, we say that no support structure is required. So that is true for lighter parts, lighter material, but as we are make or like less complex features, as the complexity increases, many a times some or the other form of support structure is required even in the powder bed fusion based processes. Coming to the limitations on which we have worked, our group has worked, or rather, they have started to work in this direction. See, there is a lot of defects which are being made when we start making using the selective laser melting, because it is very high temperature heating and rapid cooling. So what it leads to is lot of shrinkage and distortion. So we wanted to make a flat product. What we get at the end, because of the uneven shrinkage, a distorted product, induced porosity. So lot of porosity, because see, when we are making powder particles go layer by layer, and then we start fusing or melting and fusing, rather not like sintering or melting and then fusing these particles. Lot of places the unfused particles are there, or sometimes there is cavity which is because of improper fusion of these powder particles. So lot of porosities can be there, which reduces the mechanical properties, and sometimes these parts cannot be used in those applications where the load bearing capacity is the critical choice. Time taking, so there is a need to make these processes faster. So not that thousands of components and we can make it in a month or so. See, many times the customer wants, or the need of the product is there to be delivered in a few days, few weeks. So these processes, they are time taking, and the shrinkages, distortion, and other things, they are usually like, so first and last point, they are quite related. The residual stresses which gets built up in the part, which causes distortion and which leads to lot of other defects also. So these are some of the issues which are there, which hamper the choice of SLM for all the cases. So simpler geometries like this, maybe it is easier to control residual stresses or inherent shrinkage, but for complex geometries it is very difficult. So how can we do that? First, we need to understand what are the physical phenomena which are happening in the SLM process. We can try to control these physical phenomena by changing the input parameters like laser beam or laser parameters, or the powder parameters. So these are in our hand. What are the things which are in our hand? Laser parameters, the powder parameters, the environment that is presented. These are in our hand. But once we set all these things, then the physical phenomena which are listed here, they start happening as we make a track. So this figure shows that on a substrate, that is on a build plate, when let's say just first layer of powder is spread, the laser beam started from this point where my cursor is right now, and it is moving to make one single track. On this track, shown with this brown color, the powder particles which were there, they have now fused together already. So these represent a set of fused powders. So these fused powders, they are getting fused because of interaction between the laser beam and the powder material. Then what happens? Heat transfer happens. So heating from the laser beam to the powder particle. So what are the things that, like, what are the mode in which it happens? Conduction, convection, and radiation. So lot of radiation inside the powder, but than that, the radiation into the atmosphere. So a lot of radiation losses. But see, for smaller build chambers, we can neglect radiation losses. There is a phase transition. Why? Because the powder particles, they are in the powder or solid form, they get first heated up, phase change, then go into the molten state. Sometimes if the laser beam temperature at a particular location is very high, sometimes some of the particle or fraction of particles even may get evaporated. But like, we should all like have the laser beam intensity in control. But heat transfer, solid to liquid phase change, that is always there, because the solid particles expanding into the liquid phase. So this is another physical phenomena which is happening. This liquid metal flow. So when, as soon as the powder turns into liquid phase, the liquid has this tendency to start flowing. It cannot retain its shape as good as the solid particles are. So this liquid phase, even though just beginning of liquid phase, it is not superheated or something, there is a liquid metal flow in the melt pool region. So what it is? Melt pool. The key here is melt pool. There is, at this small location where the laser beam is tracing the powder bed, there is a formation of melt pool. And this melt pool, inside that melt pool region, there are so many things which are happening. One of that is liquid metal flow inside that melt pool. Evaporation also sometimes of liquid metal, which is just at the top. So the topmost points or topmost layer of the powder, there may be some amount of evaporation. Because of this molten metal flow, the Marangoni effect, I'll in the next slide tell what this Marangoni effect is. It is concerned with the difference in the surface tension of the liquid metal which is there in the melt pool. So because of that Marangoni effect occurs, the Fresnel reflection. So this laser beam, so any light source, when it goes into a medium, it goes through internal reflection, and it is more prominent here because in between the powder particle there is lot of places where the laser can go inside and then can get internally reflected and then come out. So this Fresnel reflection is another physical phenomena which is happening. And keyhole formation. Many a times in this, I'm coming back to this slide. Many times what happens that in the powder, this SLM based products, there are deep holes which are created because of the keyhole formation. So keyhole formation is the formation of long cavities because of the internal reflection of these laser beams inside the powder bed. So like, as we keep building this layer by layer, the laser beam can keep on internally reflected in very small keyhole like places. So our group has worked extensively. I'll show some of the work in the next slide, in understanding this melt pool formation, considering this heat transfer, conduction and convection mode, neglecting the radiation, also considering the effect of Marangoni. So in the next slide I will tell, and also how this keyhole formation takes place, and because of this Fresnel reflection. So first thing first, this melt pool, which the researchers they say that if we want to improve the process, we want to understand first the process and remove all of these defects. We should understand what is in the gene of the SLM. So how the part quality, how the part gets made, it all depends upon this gene, and the gene is named as melt pool. So this melt pool, if we control, we can control part distortion. We can also control unwanted porosity, undesired residual stresses, poor ductility. So many times the parts which are made using SLM techniques, they are quite brittle, not as ductile as we want, and surface irregularity. So another defect which is balling effect. Okay, maybe while I'm telling about the Marangoni effect, I'll tell about this also. But balling effect is another issue with the, because it happens because of the surface tension of the liquid flow of the liquid metal in the melt pool. So all of these things can be controlled using what that is a melt pool. Melt pool is the reason. So this is, let's say, the part that the layer which we are making, so this dark portion, and the melt pool at any instant is the place where the material is present in the molten form. Outside these melt pool locations, the metal is either in the solid form, or sometimes just along the edge in a mushy zone. Mushy zone, like both solid as well as in liquid. But this portion, melt pool, is in the liquid or molten form. It has length, this width and depth. So if we control this length, width and depth of the melt pool, first we need to understand how it gets formed, and then if we can control this using our input set of parameters, as I have told in the previous slide, then we can make our part defect free, 100% defect free, if we understand the gene of the SLM. What are the process variables? Laser power, scanning velocity, spot diameter. So spot diameter, this laser spot diameter. So the laser has a certain radius and over which it is incidenting on the powder bed, laser spot diameter, and the layer thickness. How do we model? We model for this based upon the thermal history of the part. So we first calculate how much energy has been supplied to this area or the powder layer. Then we find out the melt pool characteristics. And once we know the thermal history and melt pool characteristic, the second level of modeling is for predicting the residual stresses, the part distortion, and also we can predict directly the mechanical properties using the analytical formulation or using the numerical simulation. Once we do all this, that means we can go back to this process variables, modify and get different properties. So we can keep iterating on getting the final result and going back, tuning all these process variables, and then coming in again to get the better set of properties, or reduce, like in terms of residual stresses, we want as low as possible, part distortion as less as possible, and the mechanical properties are as high as possible we want. So all these things can be done by understanding the melt pool. So as we said, this melt pool, it depends upon the energy density primarily, because this is the first laser power. So laser power it depends upon the energy density. P divided by V into L into H. V is the scanning velocity, L is the layer thickness, and H is the hatch spacing between the two laser scans. Usually the residual stresses, why it gets formed, it is because that during heating the underlying solid layer does not allow. So while the powder layer is getting heated, this top surface of the powder, it receives the laser heat. it tries to expand. However, the bottom portion of the powder, which is not heated because it is a quick process, there is hardly any time for conducting it throughout this powder layer. So the torsion tries to expand, the bottom portion of the layer tries to contract. So during heating, the underlying solid layer does not allow expansion, which induces compressive stresses. After cooling, the top layer cannot undergo complete contraction due to the pull by the surrounding cold solidified region. So tensile stress, compressive stresses, both type of stresses are there, and which builds up the residual stress in the powder layer, and which leads to distortion, and which leads to past distortion later on if the residual stresses are not relieved. Okay, so this, the other effect that I was talking about was Marangoni effect. So usually what happens, this surface tension, positive surface tension or surface tension, what it does, it tries to retain the liquid drop intact. So you just think of a surface on which if the oil is spread, so oil particles, they try to kind of retain their shape. So they try to kind of this positive surface tension, so like they try to retain the shape of the let's say here it is melt pool and the top surface. However, because of the high intensity laser, it causes, what it does, it causes large temperature gradient. So on top very high heating, on bottom the heat the temperatures are not as high, which leads to differences in the surface tension. So on top, suppose if it is expanding or trying to like the surface tension is in other direction, that it is expanding, the bottom portion is trying to contract. So because of this, the metal fluid flow happens inside the melt pool itself. So here if you see, here also there is a motion of fluid inside the melt pool, which is known as, because of this high temperature gradient, this movement is known as Marangoni effect. Fluid flow inside the melt pool because of the difference in the surface tension at the top and at the inside of the melt pool. So using all these process variables, what we have done, thermal based analysis based upon the moving heat source, analytically modeled moving heat source with appropriate boundary conditions, and we have taken proper the starting geometry, you will show in the next slide, the initial thermal conditions, and also we have taken the thermal properties which are temperature dependent, because here there is a lot of change in temperature as well as change in phase. So the thermal properties we cannot take as constant. So we have taken temperature dependent thermal properties and conducted a thermal analysis. Based upon the thermal analysis, we have predicted the temperature history of the part for different laser scans, different laser scan velocity and different lasers parameters. Then based upon this temperature history, we have conducted the mechanical analysis to predict the stress evaluation, analytical stress evaluation to predict the residual stresses, and also the mechanical properties of the final part. So we have done this in these stages: the development of a computational analytical model to simulate the physics of the SLM process, incorporating all process variables, which delivers results at inexpensive computational resources. So like this is an analytical model which does not take much of time computationally to predict the results. Here the analysis is done in two-dimensional. However, the process is a three-dimensional process. So if we see this melt pool, so all throughout we have tried to understand the melt pool, how the melt pool formation takes place for given set of parameters. So melt pool, as we have seen earlier also, that it is a 3D thing. So it has a length from here to here, width, and also depth. So the analysis which we have conducted, our student group has conducted, it is a 2D analysis, whereas the melt pool is 3D. So what we have done is that we have done the analysis in two phases, so that we can first predict the, from using the this side view, we can predict this width and depth, half width and depth of the melt pool, and using the front view we can predict the length. And once we combine this half width, because we have just cut this section, so other half is on the other side, so we have cut this section of melt pool from here, and this is half width, other half width is on the other side, which is cut away. So this half width, depth, and length. So we will do this thermal analysis for both side view as well as for the front view. Then we will combine our analysis to get the information about the length, depth, and width of the melt pool. So this there were, like, see, in any analytical model there are so many assumptions. So few of the assumptions, they are listed, like the top layer of the part remains flat throughout the simulation process. That means there is no unevenness in the powder spread. And during this no, like, say, initially the Marangoni effect was neglected in this analysis, and later on the other results they show including the Marangoni effect also. The radiation loss has not been considered, as I mentioned earlier also. The powder layer has been treated as a continuous medium with properties of the powder phase. So we have modeled it as a like, while making the computational layer, we have made it as a solid, but the properties that are given is a powder phase properties. And the heat input that has been considered as a Gaussian volumetric heat source. So, like, this is particularly more interesting for those who are doing welding studies at SLITE, because SLITE is very well known for welding related researches. So in welding, usually this heat input source that this like that is taken for modeling is Gaussian volumetric heat source, and the same thing we have also taken in our analysis. So this shows a Gaussian semi-ellipsoidal laser heat source, which delivers the heat in XYZ as it is shown here, with the kind of ellipsoidal. So like this, A the major axis, B the minor axis, C the depth part of the source, and this semi-ellipsoidal Gaussian laser heat model is shown here. And using this Green's function for conduction, the increment in temperature based upon this P, V, A, B, C, these input parameters, it has been calculated for different time instance for this domain. So this solid substrate, and then we have considered a first powder layer on top of that. This is the direction of laser movement. These green colors, they represent convective heat loss also we have considered. This red means like the powder layer thickness, and then initial temperature T naught, base plate temperature TF, ambient temperature is T infinity. So some values. So all these are taken as the initial and boundary condition. And this analysis was done till there is quasi-static melt pool formation. Quasi-static means see, when the this laser starts scanning, there is a change in melt pool depth or melt pool dimension. Excuse me. So what it is done is that as soon as the melt pool depth stabilize, so along those length only, so the results are measured, so that the quasi-static, that means the melt pool formation has stabilized. So this conduction, convection, cooling using finite volume method, and alternating direction implicit technique, ADI technique, is used for the this comparison of the stabilizing of melt pool using a Thomas algorithm solver we have made, and the prediction I will show in this slide. We have been able to predict this melt pool geometry, so half width, depth, and from the other view the length of the thing, and this melt pool boundary, what it represents. So here in this figure, if we see this mushy zone means here, if you see, there is a temperature line 1609. So thermal simulation for inconel 718 material with a melting point we have put as 1609. So just uh, above those temperature, this is all in the melt pool in the molten stage, in the fluid phase, and below that, just below that, it is in the mushy zone, that is liquid and solid phase, both of the phase in a mixed solid liquid form. It is there, and then see, much far from there it is all solid. Much inside that, if we go, it is at a higher temperature, much higher temperature, but below the evaporation temperature. So it is all available in either liquid or in superheat form, which is which is a melt pool formation, like which shows the melt pool formation and melt pool geometry. So using this analysis, we were able to predict the melt pool dimensions. Excuse me, I'll just take some water. Yes, so that was the first part. So based upon this, what we can get is that temperature distribution for each melt pool. Once we get for each instance for this any melt pool, what it can be expanded it that for the entire length of the scan we can get the temperature history. So I'll just going back a little. So thermal analysis gives us this temperature in history, and then it is followed by mechanical analysis. Okay. So after this thermal analysis, temperature history, this mechanical analysis is done to understand that what happens when the temperature, when the laser moves away from the source, the temperature starts decreasing. That is known as cooling phase. So heating followed by cooling, and the like while it is cooling, and then the temperature is distribution, which is at the beginning of the mechanical simulation, where we want to calculate, because of the rapid heating and cooling, what are the temperature based stresses that are induced. So for this mechanical analysis,
Sir,
one, yes,
sir, which software you used for this mechanical simulation?
like this is all coded in MATLAB.
Okay, sir.
Yes. Yeah, based upon all this formulation, so it is coded in MATLAB. So yes, correct. This after cooling, or like during cooling, these mechanical stresses, because of different in temperature gradient, they start building up. So the first assumption is plane strain condition, which is quite true, because like see, this melt pool or even the laser scan is quite small, is happening at a very small area as compared to the size of the powder bed. So this plane strain condition is quite valid, like it does not change the analysis much. The surface remains planar after deformation, and the surface is treated as traction free. It is little like kind of contradictory, but like initially there is no surface in planarity, like it is all plane. Pure isotropic hardening is assumed with yield surface expanding or contracting uniformly. So usually in metal forming simulations, any like even in extrusion or in forging, we take this kind of assumption that isotropic hardening, so that all the places when the yield or flow stress is expanding, yield area is locus is expanding, it is expanding uniform without any anisotropy, and because of that this Bossinger effect is also neglected. So what we have tried to find is all the principal stresses, sigma xx, sigma yy, sigma zz, and one the shear stress that is around xz plane, so zx plane. So that is all we have tried to find based upon the temperature history and the like heating and cooling cycle. And those regions which are having this value of this elastic plastic coefficient, that is f, the greater than 0, so those are in the plastically deformed zones, and the less than 0, it is in the elastically formed zone. So we have tried to distinguish all those zones where the plastic strains are there and where the elastic strains are there, and based upon this the melt pool region, see this is all plastically changed, plastically deformed in that, and then all the regions which are far away from there, it is in the elastically formed regions with almost no stress. So what will happen, like these stresses which are built up, they try to relax, whereas there is no stress built up here, it will try to resist, leading to the residual stress formation. So this residual stress distribution because of cooling slowly. So if you see, it is all cooled up to the room temperature, and the residual stresses are slowly getting built up as the temperature goes down. The residual stress, finally the variation along the part depth. So we have tried to do simulation for number of layers. So once, let's say after 12 layers got deposited, the surface, like the along the like just this 0 shows the surface. So along the part surface, just at the surface, the residual stress is very high, tensile residual stresses. However, see, as we go down, the nature of residual stresses changes. Sometimes it goes immediately into the compressive residual stresses, but a large, very huge residual tensile residual stress at the top surface, which is unwanted. Why it is unwanted? Because tensile residual stresses can lead to early fatigue failure. So the fatigue critical applications, need to be we need to make sure that the tensile residual stresses are not there. Rather, compressive residual stresses, if they are there, they are very good, like very good, because the fatigue life in gets improved if the compressive residual stresses are there in any part. So many times you might have seen that a typical post processing for metal based products is short peening. So once the products are made, then they are short peened. However, the objective here is that we tune the laser parameters or process parameters to get the minimum possible residual stress. Similarly, like so, this is sigma xx component only. Sigma yy component also shows, like it shows on the top surface there is compressive residual stresses. uh, See, with these results, like sometimes like these numbers, they may be misleading. What we try to find out that what are the effect of different process parameters with our analysis for residual stresses as well as for the temperature distribution. So this what we have found that as the laser power increases, the energy density increases, P increases, and rest of the things, if they are constant, energy density increases. That means the input energy to a particular place of powder increases, at any particular location of powder increases. What it leads to is increase in melt pool dimensions, length, width, depth. However, the cooling rate goes down, the residual stresses goes down. So what we have observed using our results, and then the same thing was observed by a few other researchers who have conducted either numerical simulation or the experimentation, that As we increase the laser power, the width and depth of the melt pool, it keeps on increasing. So this is what like that means if we want smaller melt pool to be found, we should go with lower laser power values. However, lower laser power might lead to higher residual stresses. So the residual stresses for different laser power, if you see, so 300-watt laser, uh, the residual stresses, they are least with 100-watt laser, but keeping all other parameters the same. So not that only one parameter can be changed. We can change other parameters also and see the effect. I will show in the other slide. But if we keep all other the same, the effect of the laser power, it is increasing the melt pool density and reducing the residual stress formation. Effect of scanning velocity. So the other thing, which is V, scanning velocity. So now we are keeping the P and L and H the same. We increase the V, energy density decreases, input energy decreases, the melt pool dimensions, they decrease, and cooling rate increases, residual stresses have been found to increase. So as we increase the scanning velocity, however, see, there is stability that is coming. That means after a particular set of scanning speed, there is hardly any change in residual stress. So it is getting stabilized, the maximum residual stress. The other thing, so three things. The other thing that we have changed is changing the layer thickness. It has reduced the heat loss. Melt pool dimensions have gone down, cooling rate have gone down, residual stresses have gone down. So if we increase layer thickness, it is better. Residual stresses are coming down with increase in the layer thickness. So like some idea we have got how to control the melt pool dimensions and also how to control the formation of or building of residual stresses inside the powder material while it is getting heated, melted, resolidified, and so on for different set of process parameters. The other thing was to see it for different materials also. So just not for in Cornell, our group has tried for this popular material TI6AL4V, which is a common biomaterial like for bioplant and so on. It is used. So what we have observed that larger melt pool for material with low melting point. So TI6 has higher melting point. So low melting point material leads to, we can see from here. So low melting point temperature material, then the larger melt pool material, large melt pool dimension with high melting point, smaller melt pool formation. Higher cooling rate with cooling rate has been obtained for material with greater thermal diffusivity. So the thermal diffusivity of Inconel is low. The thermal diffusivity of titanium is high. So higher cooling rate for higher thermal diffusivity. We can see from this here. And also the material with higher yield stress suffers greater residual stress. So TI6L4V has much higher yield stress, and also it has a very high residual stresses built up in the part. So with choice of material also some recommendation can be given. Suppose a part can function with few material options given, we can, if we want lower values or lower residual stresses built up, we can recommend that material with lower yield stress is preferred because it would lead to lesser built up residual stresses and so on. So like all these process parametric analysis might help us in understanding, recommending a proper material, a proper set of process parameters, and also the formation of melt pool which is kind of in key of all these things, we can understand that better. So like key points of like this is not the overall conclusion. There is something still left. So this particular part of this work, what it found was that the semi analytical model, which gives us a very good results in terms of melt pool dimension, stress generation for different set of process parameters like laser power, scanning speed, layer thickness, beam diameter. So we have varied we beam diameter also have not shown those results, and number of layer deposition for different a number of layer definitely gives us very good results, and it is quite fast also. However, let's see, conducting the simulation always or analysis always using complex mathematical formulation is difficult. So what we thought later on that if we somehow can build a artificial neural network based model based upon the input parameters and the data that we have got from our analysis. So see, this analysis has given us a lot of data for different input parameters. So what we found that the for a given material, if we can get analytical model lot of data for different laser power, scan speed, laser thickness, and we can anyway we have values for melt pool depth, width, and melt pool length. We can easily predict using an artificial neural network model for different situations. So our group tried for making all this simple artificial neural network based model with feed forward, back propagation network, and this tan sigmoid based transfer function for hidden layer, and purely linear Purelin function for